Yeah, there is a discussion of bound state and scattering state, okay, the next topic in Griffiths. But I'll take this one a little bit later because one more topic should be covered: probability current density, continuity equation in quantum mechanics, okay? Continuity equation in quantum mechanics. Only after that one, I think that bound state, scattering state, that idea can be convinced, okay, properly. And let me do that one tomorrow morning, okay? So tomorrow we shall have a class, okay, morning. Yeah, one more bound state. Bound state means, look at here, particle cannot escape to infinity. In case of free particle can go to infinity, isn't it? I mean, so there is no boundness over there, okay? Again, in case of harmonic oscillator, or in case of particle in a box, or if you take hydrogen atom, those we call them as bound state, okay? And there is one more bound state problem here, and that is Dirac function well, okay? It's a quite hypothetical potential, okay? Dirac function well, the Dirac function well. Our potential is, again, we have already discussed about Dirac delta, okay? I'll not discuss about that one again. Our potential is V of x is equal to minus alpha into delta of x, where alpha is positive and real. Is that okay? Minus alpha into delta of x. If you want to plot this one, V of x as a function of x, okay? You have negative sign here, that's why at x equal to 0, you have negative spike. Can I say like this? Symbolically, we draw it like this, and it is 0 in other region. The value of the function is 0 in other region. Is that okay? V of x is equal to minus alpha into delta x. Negative sign. Speak out. Now look at here, when you take a Schrodinger equation, minus h bar square by, now look at here, what is the range of Dirac delta? Minus infinity to plus infinity, okay? Whenever you take Dirac delta, what is the range of this potential? Minus infinity to plus infinity, okay? So now, minus h bar square by 2m d square psi by dx square minus alpha into delta of x, okay? Minus alpha into delta of x is equal to into psi is equal to E into psi. Am I right? This is our Schrodinger equation. Now so there are two situations that may happen. What is the minimum value of the potential? What is the minimum value of the potential? What is the minimum value of the potential? Pick up. Not 1. So look at here, that means V of x is equal to, look at here, it's equal to minus infinity. When x equal to 0, it's equal to 0 otherwise. That's the meaning of that minus sign. So that's why that is minus infinity. So that's why energy can be any negative value also in this situation. Is that okay? And energy can be positive also, okay? And that energy negative, E less than 0, we call that one as bound state, okay? Again, you will understand this bound state idea a little later, okay, in the tomorrow's class. Energy less than 0, we call that one as bound state, okay? Energy greater than the 0, that can also happen. We call that one as scattering state. Particle can escape if energy is greater than 0, okay? If energy less than 0, particle will not escape anywhere, okay? You will get some normalizable solution. In this case, you will not get normalizable solution. You will see later, okay? So now, our bound state, again, Dirac function well, again, we are discussing bound state here, okay? Bound state, okay? The situation is E should be less than 0. I'll explain this one tomorrow, okay? Why, why E less than 0 should be bound state, E greater than 0 is not bound state like that, okay? Let me explain tomorrow. But E less than 0 is a possible energy, okay? Why? Energy should be greater than V minimum, that's it. V minimum is minus infinity, that's why energy can be negative here, okay? That negative energy states are bound state here, okay? And we shall see how many states we can find and how. Yes, tell me. No, again we shall discuss about bound state and scattering state tomorrow, okay? Right now, again I need to take much more idea, isn't it, to explain that one. You know that one, I think you are asking because of that.
Okay, sir.
So classically also this is a bound state actually, but that's again let us discuss that one tomorrow. So now this is very similar to your particle in a box or harmonic oscillator problem, okay? Is that okay? Yeah. Now look at here, E equal to E less than 0, that's a thing. Now when E less than 0, when E less than 0, look at here, if X is strictly less than 0, if X is strictly less than 0, let me solve the Schrodinger equation. If X is not equal to 0, this part is 0, isn't it? If X is strictly less than 0, not less than or equal, okay? If X strictly less than 0, I mean in the negative X axis, okay? Your Schrodinger equation is minus h bar square by 2m d square psi by dx square is equal to E into psi, am I right? Rewrite this one, d square psi by dx square plus 2m E by h bar square into psi is equal to 0. Can I write like this? Is that okay? Now since energy is negative, this total quantity is negative here, observe that one, okay? No, alpha is, if alpha is negative, this will become positive Dirac delta, okay? That's why I have taken alpha is positive. That means I want to keep this negative sign, okay? That's why I have taken alpha positive, okay? If alpha is negative cancel, it is a positive Dirac delta.
Alpha is integer or what?
Alpha need not be integer. Alpha is any real positive value, that's it. If alpha is negative will get cancelled, it will be this kind of Dirac delta. That's what I'm saying. I want to have Dirac function well here, okay?
Sir?
Yes.
Sir, for E less than 0, delta x equals to 0.
Yeah, delta of x equal to 0, am I right? When E, no, not E less than 0, for x less than 0. I'm talking about this region, okay? So this is the bound state. We are solving for a bound state, okay? And for x less than 0, okay? Delta of x equal to 0. Because x less than 0 means x not equal to 0, isn't it? That's the definition of Dirac delta. You are Schrodinger equation. But be careful here while writing k square or something. So this is negative quantity. So that's why what I do here is d square psi by dx square minus of minus 2m E by h bar square into psi is equal to 0. This is positive quantity inside the bracket. And I call that one as kappa square, not k square. D square psi by dx square minus kappa. Is that okay? Where kappa is equal to root of minus 2me by h bar, which is real, okay, not complex, because energy is less than 0, that we have taken, okay? Be careful here, okay? You have positive, but this whole quantity is negative. Don't write it as square of something, okay? Square of some real quantity cannot be negative, isn't it?
Is it possible that energy is less than 0?
Yeah, that is again, that's a possibility. Whatever theorem says, energy should be greater than V minimum. That's a possibility, isn't it?
V minimum means
minus infinity. Yeah. Is that okay? We are not talking about free particle here, okay? We are not talking about a particle with some kinetic energy or something. We can't talk about kinetic energy. You will see that one later, okay? I mean, if energy is greater than 0, then only you can talk about some particle which is moving like that, okay? This is a kind of bound state, and it's quite hypothetical one, but it is very helpful to understand lots of things here, okay? As well as we have application also in case of your particle. You can apply this one to in case of what is that, Bloch theorem. You can take this kind of idea, okay? Yeah. Now look at here, d square minus kappa square of psi is equal to 0. Your auxiliary equation is d square minus kappa square is equal to 0, d is equal to plus or minus kappa, not plus or minus I kappa. Okay, d square is equal to k square, d is equal to plus or minus kappa, and your solution is, look at here, a e power kappa x plus b e power minus kappa x. So observe this solution. We are in the region x less than 0, am I right? We are in the region x less than 0. When x less than 0 region contains x tends to minus infinity, am I right? This region contains x tends to minus infinity. Minus infinity is there in that region, am I right? So that's why in this one, if x goes to minus infinity, this is blowing up. This is becoming infinity, e power minus of minus infinity. Kappa is positive, okay? So that's why again we are going to choose b equal to 0 here. Because if b exists as x tends to minus infinity, this will go to infinity, this will not be normalizable. Is that okay? Speak out. That's why we are going to choose b equal to 0. Because as x tends to infinity, as x tends to minus infinity, e power minus kappa x tends to infinity. So that's why we need to avoid this term. That's why I am choosing b equal to 0. After solution of any differential equation, this a and b should be found by some physical condition, am I right? Kind of boundary condition. You can take boundary condition is as x tends to minus infinity or plus infinity, wave function should be 0. Okay, this is the boundary condition. Okay, as psi should goes to 0, this is the boundary condition. Okay, so then only it will be normalizable, am I right? Square integrable function, we said like that. So that's why I'm going to choose b equal to 0. Psi at x less than 0, okay, that's equal to a e power kappa x. Is that okay? If I do the same calculation for x greater than 0, do it later. Same thing will follow. Then also delta of x is 0, e less than 0, everything. But here, let me put, okay, wait a second. So shall I rub this out? We are talking about bound state, okay? E less than 0. So psi of x, when x is less than 0, so that's equal to a e power kappa x. I got the solution, okay, where kappa is given in this one, okay? Now, when you take x greater than 0, exactly same thing will happen. Delta of x is 0, I mean strictly greater than 0. Then also delta of x is 0, same thing. But what I do here is when I come here, I'll take some other coefficient because psi is equal to some a, b, I have taken c e power kappa x plus d e power minus kappa x. I'm talking about the region of positive x-axis, okay? Now come to this point. As x tends to plus infinity, this is going to infinity. This is going to 0, isn't it? That's why I need to avoid this one. As x tends to minus infinity, this is going to 0 actually, okay? In the x less than 0 region, okay? As x tends to minus infinity, this is okay. Other part was not okay. That's why I have chosen b equal to 0. So similarly, as x tends to plus infinity, because I am talking about the region x greater than 0. In the region x greater than 0, plus infinity will come. As x tends to plus infinity, okay? This goes to infinity, this goes to 0. That's why I need to avoid that one. Let me choose c is equal to 0. So that's why psi at x greater than 0, that should be equal to some d e power minus kappa x. Can I write it here? Speak out. I got the solution at x less than, for x less than 0, for x greater than 0. At x equal to 0, we still don't know what is happening here, okay? Be careful. Now look at here, wave function should be always continuous, am I right? See Schrodinger equation. I better to keep Schrodinger equation somewhere. Because that will give us lot of ideas, okay? Yes.
So in this case,
Yeah, speak out.
so the particle can move from h equals to minus infinity up to h equals to 0.
No. Here it's not a free particle, okay? We can't say it is moving freely, like it is propagating, like that, okay? It's a bound particle. It's a kind of hypothetical potential, Dirac function well, but it will give us more other type of information. Just wait for a while, okay? You can't think about particle is moving or something. You can only talk about probability of finding the particle, isn't it? That's what quantum mechanics says, isn't it? Again, mod psi square will talk about probability of finding the particle. You can't say much about it, okay? See, dx square, yeah. Now let me rewrite this one, okay? That's the best idea. D square psi by dx square, that's equal to, speak out, minus 2me plus delta alpha delta of x minus e. Am I right or not? Right or not? Is that okay? Second derivative is Dirac delta. Can you see that one? Second derivative of psi is Dirac delta, okay? So that means first derivative, what first derivative should be? Can you imagine? If second derivative is Dirac delta, what first derivative should be? Step function. Step function derivative is Dirac delta, okay? So that's why first derivative will be kind of step function, okay? But psi will be continuous actually. Psi will be always continuous. That's the rule in quantum mechanics, okay? Psi will be always continuous, okay? Now let me take many ideas here, okay? Many properties can be studied here, okay? So that's why psi should be continuous. That's why look at here. So limit x tends to 0, psi of x as x less than 0 should be equal to limit x tends to 0, psi of x as x greater than 0. Am I right? Let me write x tends to 0 minus x tends to 0 plus, isn't it? You have wave function for x less than 0 in the negative x-axis approach 0. And you have wave function at x greater than 0 in the positive x-axis approach 0. And these two should match. When you put 0 here, x equal to 0 here, those two should match. That's why A should be equal to D. Is that okay? And look at the wave function right now. Right now, look at the wave function. Okay? So psi of x is equal to, that's equal to, since A equal to D, let me take A in the both side. Okay? A e power kappa x when x is less than 0, A e power minus kappa x when x is greater than 0. When x is greater than 0, it is minus kappa x. When x is less than 0, this x is replaced by minus x. Have you seen this one anywhere? Speak out. How do you write this one? Speak out. Mod x is between minus infinity to plus infinity. Can I write my wave function like this in both regions together?
Yes.
So continuity of the wave function give us A should be equal to B. Okay, continuity of psi wave function should be continuous. Okay, but I'm not saying derivative is continuous. Okay, be careful. I'm not saying derivative is continuous. Derivative will be discontinuous. Okay, then only second derivative can be Dirac delta. If derivative is discontinuous, if first derivative is continuous, second derivative will not be Dirac delta. It will be some what you call real kind of value, isn't it? Derivative will be discontinuous. You can observe by seeing the Schrodinger equation itself, because we have done something related to Dirac delta. Am I right? So now my wave function for this potential for bound state is less than 0. So psi of x is equal to A e power minus kappa mod x, where x is between minus infinity to plus infinity. Is that okay? Now can you normalize later? Mod psi square integral minus infinity to plus infinity. We have done this kind of problem, right, in the earlier chapters, because So this kind of questions were there actually. Can you normalize later? Mod a square minus infinity plus infinity e power minus 2 kappa mod x dx is equal to 1. You can convert this one into 2 times, isn't it? Can you plot this one? I think I have plotted this one also several times, am I right? This one, this kind of curve. It has a sharp edge here, okay? E power minus kappa mod x, okay? Whenever you have sharp edge, function is continuous, but derivative will be discontinuous, okay? That's what we have said. So, I mean, you can find this one, this will be root kappa, okay? Just check this out. So, normalized wave function will be root kappa e power minus kappa mod x. Let me write normalized function, or you can put it here, you can find that one, okay? Okay, we found normalized wave function, but what is the energy, isn't it? We haven't found energy at all in this situation, isn't it? Now, to find energy, what we do is, again, we will go for, its derivative is discontinuous, am I right? That we have seen. So, when you take the slope, your slope is some value here, some negative value here, when you approach x equal to 0, okay? So, from this side, your slope has some other value. Is it okay? When you approach from this side, your slope has some negative value. When you approach from this side, slope has some positive non-zero value. When you approach from this side, your slope has some negative non-zero value. Can you see that one? When you just zoom in, isn't it? You will have like this kind of slope when you approach from here. When you approach from here, you will have this kind of slope. Slope means derivative. Derivative is discontinuous actually. Okay? So, can you try to plot derivative function d psi by dx? That will be, can you plot? In this region, e power minus kappa x, am I right? So, its derivative is e power kappa x only. Isn't it? It will be this kind of curve. So, in this region, it is e power minus kappa x, minus will come. I think it will be this kind of curve. Check this out. If I am not wrong, okay? Derivative will be discontinuous. That's what I was trying to say, okay? Just try to do that. Try to plot d psi by dx, okay? You will understand this one. Now, we need, look at here, if you take derivative, I have plotted this one. Try this one, okay? I'm not sure about this one. I hope I'm right. Anyone? Comment? Okay? How much discontinuous it is? I need this height. So, when you take derivative, when you approach 0, you have one value, okay? From 0 minus, okay? When you approach from 0 plus, you have other values, isn't it? And I need the difference of those values actually. I need this height. How much discontinuous derivative is at x equal to 0? I need that amount of discontinuity. Okay? To find that one, we go for Schrodinger equation itself. Okay? Let me take this Schrodinger equation. Minus h bar square by 2m, okay? d square psi by dx square minus alpha delta of x psi is equal to psi. I have already written. What we do here is we are going to integrate this Schrodinger equation within a point minus epsilon to plus epsilon, where epsilon is positive. Okay? In the neighborhood of 0, we are going to integrate this equation, whole Schrodinger equation. That is minus h bar square by 2m, look at here, minus epsilon to plus epsilon, d square psi by dx square into dx, okay, minus alpha into integral of delta of x into psi of x into dx, integration between minus epsilon to plus epsilon, okay, equals to integral of E outside, integral of psi dx minus epsilon to plus epsilon. I have integrated Schrodinger equation in the neighborhood of 0 because I need how much derivative discontinuity is there, amount of derivative discontinuity. Okay, so this part can be written as minus h bar square by 2m. So second derivative integrates first derivative, am I right? D psi by dx, observe carefully, running from minus epsilon to plus epsilon, isn't it? Minus alpha, what is this one? Dirac delta will choose the psi of x at x equal to 0, isn't it? This alpha into psi of 0. This one, alpha into psi of 0. Yesterday property, isn't it? Delta of x minus 0, you can take like that, isn't it? Now is equal to E into, let me keep this one, let me come to this point in the next step. Okay, so what is this one? Observe this one, minus h bar square by 2m d psi by dx, okay, at plus epsilon minus d psi by dx at minus epsilon minus alpha psi naught is equal to E into integral of minus epsilon to plus epsilon psi of x dx. Okay, so what is this one? This is derivative at some plus epsilon, am I right? I mean positive x value, derivative at positive x value, derivative at negative x value, isn't it? So these are different. Now what I do is, I'm going to take this epsilon tends to 0. Then that will become derivative discontinuity, amount of derivative discontinuity. That means, yeah, again it's a neighborhood. Yeah, we have intentionally took that one. I hope you have written kappa. Okay. Now observe this one. Okay, your derivative curve will be like this. Am I right? D psi by dx. You have derivative at x greater than 0 here. Okay. You have derivative at x less than 0. Okay. Now when I take derivative x greater than 0, but epsilon tends to 0, but so towards 0, what I get? I'll get this value. If I put epsilon tends to 0, okay, if I put epsilon tends to 0, so d psi by dx, so when you put epsilon tends to 0, you will get into this value, limit, isn't it? So d psi by dx for epsilon less than 0, but epsilon tends to 0. Minus epsilon means, I mean negative x-axis, okay? Epsilon tends to 0, epsilon again, so x is less than 0, epsilon tends to 0 means it will give you this value. If you put minus epsilon means you are talking about derivative in the negative x-axis. If you put plus epsilon means you are talking about derivative in the positive x-axis. And if you put epsilon tends to 0, this value, whatever this value, okay, so it will approach this value will approach this value. And the difference is the, what you call, derivative discontinuity. Look at here. I'm taking the assumption that epsilon tends to 0. Okay. In the region epsilon tends to 0. Okay. In the region epsilon tends to 0, minus h bar square by 2m. Can I write like this? Delta of d psi by dx. Or you can write like this, d psi by dx at 0 plus minus d psi by dx at 0 minus, you can write like this also, one more step, okay, minus alpha into psi naught. What is this one? What is this one? As epsilon tends to 0. This was area under psi of x, am I right? Between minus epsilon to plus epsilon. This was this area. Now if you approach epsilon to 0, this area also becomes 0. Because height is finite here, okay? height is finite. If you approach epsilon to 0, this area shrinks to 0. This part is 0. So can I write like this? Speak out. Right hand side, integral of psi x dx. Am I right? E into psi was that the whole thing is integrated, okay? Whole Schrodinger equation was integrated. Speak out. Height is finite here, okay? Width is 0. Epsilon tends to 0. Height is finite. 0 into finite value, 0. Area under the curve is 0. Can I say like this? Okay? Yeah. Now, so this will give us delta of d psi by dx. I better to keep this one as it is, okay? Delta of d psi by dx. That means d psi by dx 0 plus minus d psi by dx 0 minus, okay? That is equal to, I'll take everything in the right hand side, minus 2m alpha by h bar square into psi of 0. We found amount of discontinuity. That's equal to minus 2m alpha by h bar square into wave function at 0. This will give you amount of discontinuity. This kind of questions are there in exam, okay?
Sir, what will be the integral if delta function is at some another point like delta x minus a?
Then you have to integrate in that neighborhood, that's it. Exactly the same thing will follow.
Zero, sir.
No, not 0. You have here it's a spike at x equal to 0, am I right? That's why I have integrated in the neighborhood of 0. If it is spike at x equal to a, you should integrate about that point, isn't it? Or if you want to, talk about that situation, do everything, then shift your origin, okay? You'll get that situation.
So the last integral in the last line.
This one.
Yes, sir. This will be
No, then also it will be 0. You are integrating about the neighborhood of that point, then also it will be 0, and you are approaching to that point actually from both sides. Exactly same idea. Here 0 is a point of spike, other will be point of spike, okay? All ideas will be same. That's why we can do for x equal to 0, then we can shift the origin, isn't it?
Yes, sir.
Yeah. Then again you have to write wave function at that point actually, because this will be delta of x minus a psi of x, am I right? If it is, then it will be psi of a. This result remains same. But this will not be 0 plus 0 minus, it will be a plus a minus, okay? Are you getting my point?
Yes, sir.
Yeah. So I mean this psi at the point where Dirac delta is spike, can I say like this? That is 0 in this case, okay? That's the best way to define. Now you have wave function. You have wave function, isn't it? You can find these two and substitute. Find derivative. D psi by dx when x is less than 0. What is that one? Root kappa, a kappa e power kappa x, okay? Because when x is less than 0, it is positive, okay? So can I directly write? I hope you can follow. D psi by dx when x is greater than 0 minus root kappa into kappa e power minus kappa x. Am I right? Or write down this definition at x greater than 0, at x less than 0. Root kappa at x less than 0 is equal to root kappa into e power minus kappa x when x greater than 0, okay? I have taken derivative when x less than 0, I have taken derivative when x greater than 0, okay? Now I have to approach 0, isn't it? Now I have to approach 0. X less than 0, I have to approach 0. That's why d psi by dx as 0 minus, am I right? X less than 0, x is approaching 0. That means negative limit, isn't it? So that's equal to root kappa into kappa. So similarly, d psi by dx S0 plus, am I right? X greater than 0, but X is approaching 0. Derivative with respect to X. Derivative with respect to X. Okay? Yeah. So that's equal to minus kappa root kappa into kappa, isn't it? Substitute that one. Psi of 0 is root kappa. Okay? Substitute that one. Minus root kappa into kappa minus, this is positive, okay? Root kappa into kappa, that's equal to minus 2m alpha by h bar square into root kappa. Psi of 0 is root kappa. Negative sign is also got cancelled. 2 kappa. You got kappa value. Look at here. You got kappa value. Where should I write? Two kappa is equal to this one. Kappa is equal to m alpha h bar square. What is kappa? What is kappa? Root of minus 2me by h bar m alpha by h bar square minus 2me is equal to m square alpha square by h bar square. One of the m got cancelled. E is equal to minus m alpha square divided by 2 h bar square. As expected, energy is negative. M alpha square by 2 h bar square. Or you can remember like this, E is equal to, okay, this is kappa is equal to this one, minus h bar square kappa square by 2m. You can remember like this also. That's the best way, because that kappa should be remembered for this one. You better remember E in terms of kappa. You better remember kappa. Now we got the solution. Psi of x bound state, okay? Root kappa e power minus kappa mod x, where kappa is equal to m alpha by h bar square, and your energy is equal to minus h bar square kappa square by 2m, or you can write as minus m alpha square divided by 2 h bar square. How many bound state you got? How many bound state you got? You didn't got n equal to 1, 2, 3, am I right? You got only one bound state. These are the questions actually. How many bound state Dirac function will have got, isn't it? Only one bound state. Only one wave function, only one energy. Normalized wave function, energy corresponds to that one.
Sir,
Yes, speak up.
so how you say that only one bounce?
Now look at here. For a given alpha, for a given situation, you got only one wave function, one energy. Particle can be in this state. Done. Isn't it? Your psi of x comma t is equal to psi of x into e power minus IET by h bar over. You don't have another energy state, isn't it? Only one energy state you have. Only one bound state. Is that okay?
Okay.
There is no n integer dependent and different bound state like that. Okay, only one energy. That is decided by this alpha actually, this coefficient, whatever we put here. Okay? Yeah. Now, you have to take this one. He put in what you call bracket. Psi is always continuous. Psi is always continuous, okay? So d psi by dx is continuous except at the point where potential is infinite. statement 1, statement 2, he put these two in bracket. That means you need to remember. Look at here. If you see wave function, okay, if you see wave function psi, okay, I hope I'm right about this derivative curve. Anyone? Or ulta? Kappa will come out positive.
So this is right.
This is right, am I right? Yeah. Antisymmetric. Okay. Derivative is discontinuous only at x equal to 0. Observe, not in any other value. Okay. Here these curves are continuous. Are you getting my point? And it has a sharp edge only at x equal to 0. Remember, x equal to 0 is the point where your potential is infinite. Okay. Only at that point you got derivative discontinuity, not in any other point. Okay.
Sir,
Yeah.
sir, what you have written that psi is continuous and dz is continuous except that potential is infinite. This is true for all cases.
All cases. You can take it as a theorem.
Okay.
Like actually, this is a property of Schrodinger equation. If you look into Schrodinger equation properly, so shall I close this one? Next thing is find expectation x, expectation p, like that. Okay. Next question. Okay. Wait a second. I'll talk about that one later. While finding expectation p square, be careful in this state. Why? You have second derivative. Minus h bar square psi star d square psi by dx square psi, but second derivative doesn't exist. First derivative is discontinuous. Okay, then what will you do? Our earlier idea, mod square of this one, am I right? Positive here. D psi by dx you can define, am I right? Mod square dx, split the limit and do the integral. Or I have one more technique of doing expectation p square, okay? You better remember this one, okay? For bound state, okay? I'm talking about bound state, not any, what you call, linear combination state. P square by 2m expectation is equal to mod of your energy. What is your energy? M alpha. You better to remember this one, because in exam you better not to go for calculation, because second derivative will not exist. First derivative will be discontinuous. Or you can go for first derivative and you can go for this formula, okay? If you want to go for p square by 2m, either you can go for this one, okay? H bar square by 2m plus here d psi by dx the whole square dx, okay? Either you can go for this one, or you take this one as a trick. No logic. Because that would be quite lengthy step. Expectation x you can find, that's equal to 0 actually. Expectation x square you can find, and you have done that kind of problem already, isn't it, in the first chapter. They haven't mentioned that it is Dirac function, well, wave function, okay? But for expectation p square, you should be careful. I think I told there also, isn't it? There only I told, isn't it? It has a derivative discontinuity, that's why follow this step, isn't it? That's what I told, okay? I think you can do that part of the problem. Again, I wish to discuss these things actually, because again, there are questions in TIFR exam on these properties actually. I hope you have noted down these two. Psi is always continuous, okay? But derivative is discontinuous except at the point where potential is infinite, isn't it? Now, take your harmonic oscillator potential, okay? I better to draw. What is your potential in this situation? This is like this, am I right? V of x, this is the situation, isn't it? Now let me draw, let me try to understand this one, okay? These two statements, okay? Let me go for our harmonic oscillator potential. Okay, what happened here? Let me go for harmonic oscillator potential is continuous, isn't it? Everywhere. So that's why look at the wave function. Continuous, there is no sharp edges. Derivative, continuous. Isn't it? I don't know whether you, okay, this obvious fact, am I right? Since potential is continuous, that's why wave function is continuous, its derivative is also continuous everywhere. Is that okay? Now look at here. You had the situation actually. Particle in a box where your potential was touching infinity. Do you remember? Potential was touching infinity at x equal to 0, at x equal to a, isn't it? Wave function was continuous, am I right? If I draw psi 1, let me draw psi 1, okay? 0 a here, it will be like this, isn't it? Psi 1. Have you tried d psi 1 by dx? D psi 1 by dx. No, wave function is continuous. Look at it. It is 0 here, wave function is 0 here, wave function is 0 here. It is continuous. Am I right? Continuity. Can you see this one? But d psi 1 by dx, positive slope, 0 slope, negative slope. Can I plot? Positive slope, 0 slope at a by 2. Negative slope. Wave function is 0 here, slope is 0 here. Look at here, at x equal to a and at x equal to 0, you have derivative which is discontinuous. Can you see this one? 0, suddenly some value, isn't it? 0, suddenly some value, isn't it? Your derivative was discontinuous at the point where potential is infinity, not at any other point. Is that okay? Can you remember this point? Okay, this potential touching infinity also called as singularity in the potential, okay, mathematically. Okay, if potential touches infinity, write down, it's also, if potential touches infinity at some point, we call that one as singularity, we call that point as singular point or singularity of the potential. If potential touches infinity at some point, we call that one as potential has a singularity at that point. Okay?
Sir?
Yes, speak out.
Sir, expectation of the Hamiltonian will be equal to expectation of p square by 2l plus expectation of potential.
Yeah.
But expectation of potential when the potential is Dirac delta.
No, don't apply anything there. Okay, I took that one as a trick. Earlier thing you are thinking about.
Yes, sir. Yes.
No, don't just take it as a what you call expectation of Hamiltonian. They should contain expectation of t plus expectation of v. That's equal to e. Okay, minus m alpha square by 2 h bar square. That was the trick. Okay, don't try to interpret that one.
No, sir. I'm saying expectation of potential is not 0.
Yeah, it will be. How do you take expectation of potential? You have to put Dirac delta. Yeah, it will be non-zero. It will be non-zero. Yeah, so check that out.
Minus alpha
Psi at 0. Psi at 0. Am I right? Yeah, that's correct. Expectation v is non-zero here.
Then that e will not be equal to expectation of p square by 2, no, sir?
No. But I have taken that one as a trick. If you are worrying about this one, that's what I told. Don't think beyond that one. So take it as a trick. Mod e, I put mod e also actually. I didn't put this equal to e. Okay. Just take it as a trick because you can avoid some steps over there. Okay. You have to take derivative, then you have to integrate. You have to split the limit, and then you have to integrate. You can avoid the step. Okay. Take this one as a trick. It has nothing to do with this one. These ideas are true always. Okay.
Okay.
Yeah. So try to understand whenever potential has a singularity, okay, our wave function is continuous, whether potential is at the point of singular point or any regular point, okay. But at the point of singularity, our derivative of the wave function is discontinuous. Is that okay?
Singularity means single value.
No, singularity means if it approaches infinity, we call it a singular point. complex analysis, like that. Is that okay? I think that would be sufficient for today. Now you can solve all problem regarding Dirac function well, and I think I need 2 more class to finish out this chapter. Okay. Yeah. Any question? Yes. Yeah. Speak out. Which one? Yeah, it is. This one? Yeah, it is eigenstate of Hamiltonian with this eigenvalue. Is that okay? This is eigenstate. Yeah, it includes wave function is continuous. Look at here. Here continuity is there. It is defined at x equal to 0 only. Only derivative is not defined at x equal to 0 because it is discontinuous. Okay. Now it's all because of Schrodinger equation. Okay. I have written d square psi by dx square. Okay. Is equal to I think 2m by h bar square alpha delta minus e into psi. Am I right? Second derivative is Dirac delta means first derivative should be discontinuous. Function should be continuous. Okay. Second derivative is Dirac delta some from constant. Okay. But second derivative happens to be Dirac delta. Means first derivative should be step function. Not exactly step function, but it has a discontinuity at x equal to 0. I can't hear you properly. Second derivative?
Does not exist in this case at x equals to 0.
Yeah. No. So second derivative, again, that's why second derivative is not well-defined function at all. Are you getting my point? It's a Dirac delta. Second derivative doesn't exist, that's true. Okay. But you can write that one in terms of Dirac delta. Second derivative in terms of Dirac delta, which is not a function at all actually. So whenever you again look at here, you have defined theta of x yesterday, am I right? 1 as x greater than 0, 0 x less than 0, am I right? You defined its derivative. It was a discontinuous function, am I right? You defined its derivative as a Dirac delta, isn't it? It was also discontinuous function. You should not have written its derivative, am I right? Yeah, we have defined its derivative. We defined its derivative. Defined. Dirac delta is a defined function, not any well-behaved function actually, okay? So that's why second derivative you have to define in terms of Dirac delta, just like in case of unit step function, okay? You can say second derivative doesn't exist in a pure mathematical sense, okay? So to write second derivative, I think we invented Dirac delta, isn't it?
Sir?
Yeah.
So whatever we are doing here, mostly we are doing for x greater than 0 and x less than 0.
Yeah, but we handled x equal to 0 in some other sense actually, isn't it? We again at x equal to 0, we found derivative was discontinuous. We found that amount of discontinuity.
Yeah, mathematically we can express it.
No, that gave us energy actually. That derivative discontinuous, that expression gave us energy. Is that okay? And continuity should be there. You found x at x less than 0, x greater than 0. That's why these curves should meet, am I right? Continuity of the wave function demands that one actually.